it's not like whole 30 minutes from here, I'm not sure. So that actually is the remnant of a star that blew up. That is a supernova remnant, yep. I think that might be Messier object number 1, Crab Nebula. So we saw tonight there's 2 types of star clusters. There's open clusters and globular clusters. So it's quite possible that a bunch of stars can be born in the same nebula, basically. A big old nebula is called a molecular cloud. But as we talk about stars being born, think about our own star being born. We said that the sun came about in something called the nebular theory. Same thing with other stars. So just like the nebular theory had the solar nebula, so other stars have basically a chunk of gas that's ultimately going to turn into that star, and maybe the planets that orbit that star, right? Okay. In order for the first thing that basically needs to go from a nebula into a star is it needs to be very cold. And cold, that K means Kelvin, so 10 to 30 units on the Kelvin scale. It needs to begin contracting, okay? So it is hard to tell when I put slides up like this or when you look at figures in your textbook, is that a photo or a figure? I believe that's a photograph. So you can kind of see the dark regions. That dark thing right there. If I do this, can you guys still see your things? Okay. That blobby looking thing is actually a nebula. You know that, put it this way, do you see where, it's like a Star Trek episode, you see where there's stars here, and stars in here, there's no stars seen right there. Basically that's a dark nebula that is shielding you from seeing field of stars behind it. Okay, so that is a nebula, and stars can be born, and stars are being born there. Let's see. I guess one thing I should emphasize on this slide before I move on, and I think that the video talked about this, in order to get the nugget that's going to turn into a star, you need to basically somehow, it's like if you're making a snowball, you need to somehow get that little nugget of thing you're going to make bigger and bigger into your ultimately snowball. So you need some sort of kind of stimulation outside the cloud to begin a bunch of stars to being contracted in that giant molecular cloud.
Like a shockwave from a supernova?
Like a shockwave from a supernova. Yep, that's one way. The shockwaves from a supernova. Another thing, this is kind of weird, is to think there's 2 giant molecular clouds out there, and basically where they collide, that actually can begin star birth right there too. Sometimes just a bright star, like an O-type star, can just basically radiate energy that begins those little kind of knits. So those are 3 ways. Yep. So what do we have here? So again, this would be a photograph of a nebula. And what your author's done is to try to kind of take a region and blow it up. So it's kind of hard to see, but this region is kind of a blow up. Now, oftentimes we look for, and we heard that term on the video we watched, protostar. Okay, oftentimes we look for things like protostars in something other than the visible light. We look for it in infrared. So kind of from left to right, all this is showing you, if you read it, is basically from left, that could be your molecular cloud or your giant nebula. Okay. And then, let's see, that's the wrong color. Here, basically, this is after it's stimulated, one of those 3 ways, either like a supernova or a giant molecular clouds colliding or just a bright star. And then these knits right here, okay, that is actually regions where you could have protostars being born. And they call this like fragmentation. Ultimately, these little fragments can turn into their individual stars. So that, clusters of stars, open clusters, globular clusters, right? So protostar is like a baby star, okay? Not quite a real star. So one of the things about protostars, or actually described here, is very similar to when our own sun was formed. We said that it began rotating, okay, and as it contracted, our sun basically spun faster and faster and faster. And so that's what happens, we see around other stars. So one of the things that can happen, and we see this in protostars, is before it turns on, basically, kind of the conservation of that momentum, or what we call angular momentum, as it spins faster and faster and faster, can create these jets that go basically kind of at a right angle to its rotation. So that's kind of shown up there. And here's some pictures of some jets. Maybe. They're there. Okay, so this over here on the right, that is actually just a figure, okay? But these are photographs down here. There's two photographs of a protostar caught in action. And my thing is not cut up with my thing. Okay, so protostar is not a real star, okay? The first stage that is a real star that we're going to talk about actually is what we call a main sequence star. So Hertzsprung and Russell identified those main sequence stars as, let's see, basically it's that diagonal line, kind of in an HR diagram, kind of from upper left to lower right. So what makes it a main sequence star is kind of what we described in our sun. What makes it a main sequence star is when it turns on. So we've kind of seen with our sun, and actually now here tonight with the video and in lecture, it needs to have hot enough and dense enough conditions in its core to begin nuclear fusion. And you guys told me that's what our sun is doing. And the first step is for hydrogen to fuse into form helium. So we talked about different types of stars, okay? 7 spectral types, the OB of Fine Guy Kiss Me, the 7 different spectral types. Well, here it says a massive O and B type stars. Now that's what we're talking about. That would be the OB, okay? That's the hot stars. This is consistent with what we saw in the video and we've been talking about. They live the shortest lives, okay? The M type stars live the longest lives as main sequence stars. And that's why we can kind of have what we call that turn-off point, right? The cluster of stars. We can get a sense for how old the cluster of stars are. So this is one of the things we've talked about tonight. Basically over here, let's see. This is just, you probably recognize down here. This would be your M type. It's kind of the opposite of, I could tell it's M because they're orange, right? This would be like your O type stars. Okay, so basically they're saying how many O-type stars are there? Well, in this given number, they're pretty rare. How many M-type stars are there? Lots. Do we see them? No, because like I said, and they said they're kind of dim. All right, so the upper and lower limits to how massive a star can be. And actually we hit that in the previous chapter when we talked about characteristics of stars. We said that's that 0.08 to 100, okay? So we're going to take another look at that. If they're too massive, they basically kind of blow off some of their mass and kind of settle into something that's more normal, okay? And if they're on the light side, if they're not as massive as 8% the mass of our sun, 0.08 solar masses, then they're going to end up as brown dwarf. And I have a slide here about brown dwarfs, and they talked about that. It's basically the failed star, brown dwarf, less than 0.08 times the mass of our sun. So here is the brown dwarf. Looks a bit like Jupiter, doesn't it? Over here. Okay. I can't remember what it is, but Jupiter would have had to have been, remember, 5-6 times more its mass to have basically been a companion star to our star. All right. So basically what they're saying is the failed star, the 0.08 solar mass object, it tries to contract, But this is trying to show you this down over here, this, with this people, it's like, they look like they're playing musical chairs. Basically, it's a type of degeneracy pressure that says, all right, brown dwarf, I'm not going to contract anymore, and I'm not going to heat anymore, and I am not turning on to become a star, because I'm not hot enough in my core. Okay. All right. So again, the video emphasized that it's all about mass will actually dictate how long it lives its life, and also the stages it'll go through. So when we talk about low mass stars, and there's one exception, but in general, the cutoff is about 8 solar masses, or 8 times the mass of our sun. So anything less than that is low mass, anything higher than that is high mass, basically. That's kind of one cutoff. So if it's less than 8 solar masses, which, by the way, let's see, 1 solar mass, that's us. So we fall under this category. Our sun is this category. You saw this in the video. Right now our sun is fusing hydrogen to form helium. Okay, it's in gravitational equilibrium. We talked about that when we talked about our sun. Okay, which just basically means that gravity tries to crush it, but its energy has an outward pressure to balance that. Well, in about another 5 billion years, the hydrogen fusion in the sun's core is going to slow, because it's like playing poker or whatever. It ran out of its hydrogen in its core. Okay, and in that case, basically, its fusion is going to slow, and the fusion is what kept gravity from winning out. So gravity's going to win out, and the thing's going to shrink. I know it feels weird because it's going to shrink, but it's going to swell. Yeah, that's exactly it. Okay, so the core will shrink down, but it will expand. The edges will expand. This talks about something called, and the video didn't talk about this. Okay, this shell hydrogen fusion, this is what this looks like. So basically, in another 5 billion years, this is going to be the center of our sun, and I'm going to just write He for helium. Okay, basically our sun is going to be mostly helium in its core. If I go ahead and that's its core, well, this could be its outer edges. It's actually going to be then contracting because it ran out of hydrogen and it can't fuse helium yet. So that contraction actually can do kind of a cool thing. And I'm going to go ahead around that helium, and I'm going to make another little circle there. With those purple lines contracting, basically it can take fresh hydrogen right here. I'll put H, fresh hydrogen, that's around the core, and it can begin fusing that. So that actually, in the blue area, that shell around the helium core, actually that's where we can have this shell, hydrogen shell fusion. That's what that is. All right. So eventually, that little red core that said helium, eventually helium it'll get hot enough to go ahead and begin making carbon out of the helium, just like we saw on the video. But the whole hydrogen into carbon, helium into carbon, that's where it stops. It'll kind of try to do one more time, one more heat up, and it will never fuse carbon. It can never get hot enough to fuse carbon. So basically, what we saw in the video is it's going to end up as basically just a carbon, an orb of carbon. In the core anyway. And that's all it's going to do. And then actually it talked about, well, I did talk about it, it's not on my slide. I'll go ahead and add one thing here, and we'll be including this in notes later, but this carbon core, this actually is a white dwarf. White dwarf. That's what our sun's going to end up as. The other thing about the carbon core is, I'll just kind of go like this. Around the carbon core is that nebula. Specifically, this sort of nebula is called a planetary nebula. Oops, spelled planetary. Okay, remember he kind of talked about just kind of the stuff kind of flies off. That's the planetary nebula. All right. So I liked when he talked about the white dwarf and you saw those little, I think they were green for electrons. Basically, the electrons are what stops the further collapse of that carbon thing. Okay, so kind of recapping. Now this is a different fusion than it's doing now. Can you see how this is different? Okay, notice, and this is just kind of, the way you read this is kind of from left to right. Notice the starting material is not hydrogen, the starting material is helium. This is what our sun is going to do after it leaves the main sequence. Okay, and it's going to form carbon and release energy. And this is kind of showing you the swelling sort of part that are, this is a, top one's a main sequence. Okay, and the bottom one is after it's left the main sequence, kind of how it's going to expand into a red giant. Then over here you probably recognize your HR diagram. Okay, so over here we've got a cluster of stars. I'm going to go ahead and kind of try to focus in on, okay, that line right there is where the main sequence stars lie. Notice we see a turnoff point. Okay, that's just an indication where this cluster of stars, everything above it has left. Okay, where did it go? It went up here. Okay, and actually that's where our star is going to go. That's where the sun is going to go next. And then over time, what's going to happen is it's going to cool off, and I think it kind of goes over here, and then it kind of cools off and ends up here in white dwarf regions. I really like the word retired star because I just think that is what they are. They're retired unless they have a companion that kind of dumps on them, like we saw in the video. So there you go. So if you have, and I think you do have a homework question for this chapter that says, well, what do you mean by a star moves on the HR diagram? Well, what an HR diagram is its luminosity along the y-axis and its surface temperature or spectral type, it's the same thing, along the x-axis. So it must be changing its luminosity and surface temperature. And there's kind of the groupings on the HR diagram. Planetary nebula is the thing for a while anyway that kind of surrounds the white dwarf, the retired star. Actually, here's a couple examples of planetary nebula. So the cool thing about planetary nebula, and I like to tell people at the observatory, is you look in there, there's a retired star somewhere in there. There's a white dwarf in the center of every planetary nebula. Actually, they got the name planetary nebula because they kind of look like planets, some of them. They kind of have a little bit of a shape to them. Over time, that's just gonna, that glow's going to go away. Okay. There's another planetary nebula. Doesn't quite look like the same. It's pretty. This one's called the Butterfly Nebula. This one over here, Butterfly Nebula, Helix Nebula. So that's just kind of a gentle release of material that can actually be used for new stars. Very pretty. Okay, so remember when he said red dwarf? Okay, that's what this slide is all about. There is actually another threshold of low mass star, okay, that is, of course, low mass means less than 8 solar masses. But if it is between 0.08 and 0.4 solar masses, then actually it falls into this kind of odd sort of category. It will never fuse helium into carbon. It just won't. This is what it does. It's actually called a red dwarf. So if you kind of get your bearings, this is a red dwarf star. This, of course, we know that in the core, it is going to be taking hydrogen, 4 hydrogens, didn't we look at that the other day? basically hydrogen and converting it into helium. That's what's going on in the core. Well, these things are so low mass, they're so chillaxed, that I guess one way to think of it is they're a little fluffy. Basically, things can move within the star. We've talked about convection before. Our sun does it in our sun, it does it in our planet. That's what's happening. Basically, helium convects out and fresh hydrogen convects back in. So helium out, fresh hydrogen in. So instead of running out of hydrogen, basically it kind of just drills its hydrogen back in. Unlike normal stars, 0.4 solar masses or heavier, basically they've got a core that's kind of confined. Okay? So it's kind of a beautiful thing, red dwarfs. So eventually it ends up with, it definitely will never fuse helium to form carbon. It just doesn't have it doesn't want to do that. Okay? So it's just basically going to be an orb of helium, which helium is it's in rare quantity on Earth these days, if I understand it right. Okay. So there is a little subtle difference between low mass stars. These are really low mass stars to give you their red dwarfs. And that's how far I wanted to get tonight. All right. So I'll pick up there on next Thursday night, and I'll have can you believe there'll be time to give a review sheet for the test the next